The Mariana Trench reaches nearly 36,000 feet below the surface of the Pacific Ocean. At that depth, Mount Everest could be placed inside the trench, and its summit would still remain underwater. At the bottom lies Challenger Deep. The pressure there exceeds 1,000 times the pressure at sea level. For decades, it has been described as the deepest place on Earth. The phrase sounds permanent, as if the planet finished shaping this boundary long ago, but the crust beneath the Pacific Ocean has never stopped moving. The Pacific Plate continues to slide beneath the Philippine Sea Plate by several centimeters each year. The descent is slow, but it never pauses. Earthquakes still rupture along the boundary beneath the trench. Some fractures occur miles beneath the seafloor. Challenger Deep itself is not a single clean pit. Sonar surveys reveal a wide depression with uneven ridges and shifting contours. Different expeditions have reported different depths. Some measurements vary by tens of meters. The seafloor nearby bends downward, where the descending plate begins its dive. Sediments from the surrounding ocean floor continue to slip toward the trench. Subduction zones are among the most active boundaries on the planet. Entire slabs of oceanic crust are still sinking into the mantle below. The deepest place on Earth sits directly on top of that motion, but permanence is a strange word for a landscape that is still bending. Far out in the western Pacific Ocean, where the surface of the sea stretches in quiet blue distances between island chains, the seafloor bends into one of the most dramatic shapes on the planet. Beneath thousands of feet of water, the crust of Earth curves downward into a long, shadowed depression known as the Mariana Trench. From above, nothing about the ocean hints at its presence. Waves move calmly across the surface, winds pass over open water, and sunlight fades gradually into darkness. Yet far below that tranquil surface, the solid skin of the planet folds and descends into an immense arc carved into the ocean floor. This trench traces the boundary between two enormous pieces of Earth's outer shell, a boundary that stretches through the deep Pacific like a scar slowly etched into stone. The Mariana Trench lies east of the Mariana Islands, a crescent chain of volcanic peaks rising from the sea. These islands mark the edge of a restless geological frontier where two tectonic plates meet. The trench itself follows this boundary in a sweeping curve that extends for more than 1,500 miles along the ocean floor. Instead of forming a straight line, the trench bends in a broad arc that mirrors the slow geometry of the plates beneath it. Along this curve, the seafloor plunges downward with extraordinary steepness, creating slopes and valleys that vanish into darkness. The deepest known region within this immense structure is a place called Challenger Deep, a depression nested within the larger trench system where the seafloor reaches its greatest known depth. The origin of this vast chasm lies in the slow collision of tectonic plates. Earth's outer shell is divided into moving sections of crust and upper mantle known as plates, each drifting across the surface of the planet at speeds comparable to the growth of fingernails. In the region of the Mariana Trench, the Pacific Plate moves steadily toward the Philippine Sea Plate. The Pacific Plate is older, colder, and denser, and as the two plates converge, it begins to sink beneath its neighbor. This process is known as subduction. As the descending plate bends downward and slides into the mantle below, the edge of the ocean floor folds with it, forming a deep trough where the crust is pulled toward the planet's interior. This slow descent does not occur as a simple drop into darkness. Before the plate disappears beneath the surface, it flexes like a massive beam under pressure. The crust curves downward along the plate boundary, and the ocean floor follows that curvature, forming the elongated depression, recognized as the trench. The descending slab continues its journey deep into the mantle, while the surface above it remains marked by this sweeping fold in the sea floor. Over immense spans of geological time, this movement creates the long crescent-shaped valley that defines the Mariana Trench today. Challenger Deep rests within this curved boundary, like a quiet hollow carved into the deepest part of the trench. It is not an isolated pit, but part of a broader system of depressions formed by the bending and sinking of the Pacific Plate. Across the trench floor, depth changes over relatively short distances as ridges, slopes, and smaller basins emerge from the slow deformation of the crust. These features reveal the trench as an active geological structure rather than a static hole in the ocean floor. Ocean trenches like this appear wherever one tectonic plate sinks beneath another at a convergent boundary. The sinking plate pulls the crust downward, creating a narrow and elongated valley that parallels the edge of the overriding plate. Around the world, similar structures trace the edges of subduction zones, but the Mariana Trench represents one of the most extreme examples of this process. Its great depth and sweeping length reflect millions of years of motion between massive sections of Earth's crust. Within the quiet darkness of the Western Pacific, this immense arc continues to mark the place where the surface of the planet folds toward its interior. The trench stands as the visible expression of a process that reshapes the ocean floor itself, a boundary where the crust slowly disappears beneath the sea and begins a journey deep into the mantle below. Deep beneath the quiet surface of the Pacific, the outer shell of the planet behaves less like rigid stone and more like a vast, slowly shifting puzzle. The pieces are enormous slabs of crust and upper mantle called tectonic plates. They move with patient steadiness, guided by forces that unfold across millions of years. Where these plates drift toward one another, the boundary between them becomes a place of profound transformation. Rock that once rested at the surface begins a long descent into the deeper interior of the planet, carried downward through a process known as subduction. Not all pieces of Earth's crust share the same character. Some plates carry continents, thick and buoyant with layers of lighter rock. Others form the floors of the great oceans, thinner and composed of denser basaltic material that formed from ancient volcanic flows. These differences in composition shape the way plates interact when their slow migrations bring them together. Continental crust tends to resist sinking because of its lower density, while oceanic crust grows gradually heavier as it cools and ages beneath the sea. Over immense spans of time, this cooling makes the oceanic plate dense enough that when it meets another plate, gravity begins to guide it downward. In the Western Pacific, the Pacific Plate approaches the Philippine Sea Plate along a sweeping boundary hidden far below the ocean surface. The Pacific Plate is older and heavier, and as the two converge, it begins to slip beneath its neighbor. The leading edge of the plate bends downward into the mantle, forming a long descending slab of rock that slowly vanishes into the depths of the planet. This descent does not occur abruptly. The plate first curves gently as it approaches the boundary, the rigid lithosphere flexing under enormous forces that act across hundreds of miles of crust. This bending of the lithosphere leaves a visible mark on the seafloor. As the plate begins its downward journey, the edge of the ocean floor folds with it, forming a deep and elongated depression. The curvature grows sharper where the plate finally plunges beneath the overriding crust, shaping the long valley recognized as an ocean trench. The trench marks the surface expression of a much larger movement unfolding below, where one plate steadily slides beneath another and continues its descent into the mantle. Once the slab enters the mantle, it does not simply disappear. The descending plate remains relatively cool compared with the surrounding rock, allowing it to sink gradually under its own weight. As it travels deeper, pressure and temperature slowly reshape its minerals. Water trapped within the rock is released through chemical reactions, altering the properties of the surrounding mantle. These changes influence melting processes that can feed chains of volcanoes on the overriding plate, linking the hidden descent of crust to activity that eventually reaches the surface of the planet. Subduction therefore acts as a quiet recycling system within Earth's geology. Oceanic crust forms at spreading centers, where magma rises and solidifies along mid-ocean ridges. Over tens of millions of years, that crust drifts outward, cooling and thickening as it crosses the ocean basins. Eventually, it arrives at a convergent boundary, where its increasing density draws it downward into the mantle. There, it becomes part of the deep interior once again, transformed slowly by heat and pressure, before fragments of that material may return to the surface through volcanic processes in distant regions. Through this continuous cycle, the surface of the planet renews itself. New crust emerges from molten rock along spreading ridges, while older sections are carried downward through subduction zones, like the one beneath the Mariana Trench. The movement unfolds so gradually that human lifetimes witness only the smallest fraction of the process, yet across geological time, the effect is immense. Entire ocean floors are created, transported, and eventually returned to the mantle. Within this slow circulation of stone, the trench marks the beginning of a long downward path. The bending plate, the descending slab, and the deep forces that guide it form part of a planetary rhythm that reshapes Earth's outer shell with patient persistence. Far above the quiet darkness of the deep Pacific, a network of satellites circles the planet with silent precision. Signals pass between these satellites and instruments anchored to distant islands and coastlines, measuring the position of Earth's surface with astonishing accuracy. The shifts they detect are almost imperceptible in the span of a single day. Yet these delicate measurements reveal a truth about the planet that unfolds patiently beneath oceans and continents alike. The surface of Earth is never completely still. Among the largest of these moving surfaces is the Pacific Plate, a vast segment of the planet's outer shell that carries most of the Pacific Ocean basin upon its back. The plate stretches across thousands of miles, extending from the deep trenches of the western Pacific to distant spreading ridges near the eastern horizon of the ocean. Though its size gives an impression of permanence, the plate drifts slowly across the globe. Instruments placed on islands, resting upon its crust, show that the Pacific Plate travels several centimeters each year, sliding steadily in relation to neighboring plates. This movement becomes most meaningful where the Pacific Plate approaches the Philippine Sea Plate along the boundary marked by the Mariana Trench. Both plates move through time with their own quiet momentum, guided by forces rising from deep within the mantle. Their motions do not cancel one another. Instead, their paths bring them gradually closer together. The Pacific Plate advances toward the boundary, while the Philippine Sea Plate follows its own direction and speed. The difference between these motions creates a slow convergence that unfolds year after year beneath the waters of the Western Pacific. Modern geodesy allows scientists to measure this convergence with remarkable precision. Receivers fixed to islands such as Guam record their positions relative to satellites orbiting high above the planet. Over time, those coordinates shift by small but measurable distances. When these measurements are compared across decades, a clear pattern emerges. The Pacific Plate continues its steady advance toward the boundary where the lithosphere bends and descends. Each passing year adds only a few centimeters of motion, yet the accumulation of those small steps shapes the structure of the seafloor itself. Within a human lifetime, the movement remains subtle, hardly noticeable against the immense scale of the ocean basin. Over geological spans, however, the implications become far more profound. A single centimeter repeated year after year becomes meters over centuries and miles over millions of years. The patient drift of plates gradually rearranges the outlines of oceans and continents. Boundaries migrate, crust bends, and deep structures evolve as the relentless motion continues. This persistent movement also ensures that the region surrounding the Mariana Trench remains active rather than fixed. The Pacific Plate does not pause once the trench has formed. It continues to press toward the boundary, feeding more lithosphere into the descending slab below. As new portions of the plate approach the edge, the geometry of the boundary slowly adjusts to accommodate the ongoing motion. The seafloor flexes, faults shift, and the structure of the trench reflects the continuous supply of crust moving toward its depths. Because the plates remain in motion, the trench exists within a landscape shaped by gradual change. The boundary between the Pacific Plate and the Philippine Sea Plate behaves less like a static line and more like a moving seam stitched through the crust of the planet. Each year, the plates travel a small distance along their paths, and with that motion, the forces acting on the ocean floor quietly evolve. Across the immense timescales of Earth's history, this slow drift has never truly ceased. Satellites and instruments now capture its subtle pace, revealing the quiet persistence of a process that began long before humans could observe it. The Pacific Plate continues its patient journey across the surface of the planet, carrying the deep ocean basin with it as the boundary of the trench gradually adjusts to the steady motion beneath the sea. The rocks beneath the great trenches of the Pacific do not remain perfectly quiet. Far below the ocean floor, within the descending layers of the planet's crust, energy slowly accumulates as immense masses of stone press, bend, and resist one another. The pressure builds gradually within the boundaries of the subducting plate and along the interface, where it slides beneath the neighboring crust. For long periods, nothing visible changes at the surface of the sea, yet within the hidden architecture of the Earth, tension gathers inside the rigid minerals of the lithosphere. Eventually, that stored strain reaches a limit within the rock. When the resistance of the stone can no longer contain the force acting upon it, the crust shifts abruptly along fractures that extend through the descending slab. These sudden movements release energy in the form of seismic waves that travel through the surrounding mantle and across the seafloor above. Such events are known as deep focus earthquakes, a type of seismic activity that occurs far beneath the ocean floor within the interior of the sinking plate itself. Unlike earthquakes that originate near the surface, these deeper tremors unfold hundreds of kilometers below the seafloor. Within the cold slab of the descending plate, minerals that formed under conditions near the surface begin to transform under increasing pressure and temperature. These transformations can alter the structure of the rock, changing its density and mechanical behavior. As these changes progress, stresses accumulate within the slab until segments of the rock fracture and shift. The resulting earthquake sends vibrations outward through the planet, revealing the presence of motion far below the ocean basin. Closer to the boundary between plates, another kind of seismic event quietly shapes the structure of the trench. The surface where the descending plate presses beneath the overriding crust is not perfectly smooth. Portions of the boundary can lock together for long periods, resisting the gradual motion of the plates. During these intervals, the surrounding rock continues to move, bending and storing elastic energy along the contact between the two plates. When that locked region finally yields, the plates slip suddenly in what is known as a megathrust earthquake. During such an event, large sections of the plate boundary can shift by several meters within moments. The sudden movement alters the geometry of the seafloor above. Some regions may rise slightly as the crust rebounds, while others sink as the structure adjusts to the new configuration of stress within the plates. Though these vertical displacements may measure only a few meters in places, they occur across enormous areas of crust, subtly reshaping the contours of the ocean floor along the trench. Evidence of these changes appears in detailed surveys of the seafloor conducted after major seismic events. Instruments mapping the bathymetry of subduction zones sometimes detect slight variations in depth where sections of the boundary have shifted. These differences reveal how earthquakes can gently modify the structure of the trench itself. Over long spans of geological time, countless seismic adjustments accumulate, contributing to the evolving shape of the deep ocean boundary. The descending plate also carries fractures that formed long before it approached the trench. As the slab sinks deeper into the mantle, these inherited weaknesses can reactivate under pressure. When they slip, additional earthquakes ripple through the interior of the plate. Each movement redistributes stress within the surrounding rock, allowing the slab to continue its slow descent while accommodating the immense forces acting upon it. Through this quiet pattern of strain and release, the region beneath the trench remains dynamically active. The seafloor above may appear undisturbed when viewed from the calm surface of the ocean, yet deep within the crust, the structure continually adjusts as plates move and stresses evolve. Earthquakes provide brief glimpses into that hidden activity, moments when the planet releases the energy stored within its shifting layers. Across the immense scale of geological time, these seismic movements form part of the ongoing process that reshapes the boundary between plates. Each tremor marks a small adjustment within the deeper structure of the trench, allowing the lithosphere to continue its gradual descent into the mantle, while the form of the seafloor quietly responds to forces far below the water's surface. Along the great boundaries of the Pacific, the meeting of tectonic plates does not produce a perfectly stationary seam in the crust of the planet. Instead, the boundary itself can drift slowly across the seafloor, adjusting its position as the deep mechanics of subduction unfold. One of the quiet forces responsible for this migration is a process known as slab rollback, a subtle motion that alters the shape and position of trenches over immense spans of time. When an oceanic plate sinks into the mantle, the descending portion forms a long slab of lithosphere extending downward into the deeper interior of Earth. This slab remains relatively cool and dense compared with the surrounding mantle rock. Gravity, therefore, continues to pull it downward as it penetrates deeper layers of the planet. As the slab descends, it does not always fall straight beneath the edge of the overriding plate. Instead, its weight can draw it backward, away from the direction of the incoming plate. This retreating motion gently pulls the hinge of the subduction boundary with it. The hinge represents the region where the oceanic plate bends and begins its descent beneath the neighboring crust. As the sinking slab moves deeper and slightly backward through the mantle, the hinge of the boundary follows this motion. The trench that marks the surface expression of this hinge gradually migrates across the sea floor. Over thousands of years, the movement remains nearly impossible to detect. Over millions of years, however, the cumulative effect becomes significant, shifting the entire subduction system across the ocean basin. This slow retreat of the trench is known as slab rollback. The descending plate continues to sink, while the boundary marking its entry point drifts gradually toward the ocean basin behind it. Rather than remaining fixed in one position, the trench behaves like a flexible line that adjusts to the balance of forces acting on the slab below. The motion is measured not in dramatic leaps, but in small increments that accumulate quietly across geological ages. As the trench migrates, the geometry of the subduction zone evolves along with it. The angle at which the slab descends into the mantle can change gradually as rollback proceeds. In some regions, the sinking plate steepens its descent, bending more sharply as it drops into the deeper mantle. In other cases, the geometry relaxes slightly, altering the curvature of the ocean floor near the boundary. These adjustments influence the depth profile of the trench itself, since the shape of the bending plate helps determine how sharply the seafloor folds downward at the edge of the boundary. The migration also affects the structure of the crust above the descending slab. As the hinge of the subduction zone retreats, the overriding plate may stretch or shift to accommodate the moving boundary beneath it. Geological features such as volcanic arcs and back arc basins sometimes develop in response to this motion, recording the slow rearrangement of the plates over vast spans of time. Each of these changes unfolds gradually, guided by the deep movement of the slab far below the ocean floor. Evidence for slab rollback appears in the geological history of many subduction zones across the Pacific. Ancient volcanic chains and sediment patterns reveal that trenches have not always remained in their present positions. Instead, they have migrated slowly through the ocean basins as the balance of forces between sinking slabs and surrounding mantle evolved through time. This movement reveals an important aspect of Earth's tectonic architecture. Subduction zones do not form permanent seams, etched immovably into the crust. They behave more like shifting boundaries that respond to the forces acting within the planet's interior. The trench marks only the current position of a deeper process unfolding below. Through the steady descent of the slab and the gentle retreat of the boundary, the subduction system continues to reshape the seafloor. The trench, the bending plate, and the migrating hinge form parts of a dynamic structure that adjusts continuously as the interior of the planet carries the sinking crust deeper into the mantle. Long before a tectonic plate disappears into the depths of the mantle, the rock that forms the floor of the ocean begins to change shape. The transformation unfolds slowly across hundreds of miles of seafloor as the plate approaches a subduction boundary. What once appeared as a broad, gently sloping plain gradually begins to curve downward, responding to forces acting deep within the structure of the lithosphere. The movement is subtle at first, a gradual flexing of the rigid crust that spreads outward across the approaching plate. This bending occurs because the oceanic lithosphere behaves much like an immense beam of stone. Although solid and strong, it can still flex when subjected to sufficient force over large distances. As the plate moves toward the subduction boundary, the weight of the descending slab ahead begins to pull on the approaching crust. The leading edge of the plate starts to sag under this tension, forming a gentle arch in the seafloor that marks the early stage of the plate's descent. Just seaward of the trench, this flexing produces a feature known as the outer rise. The name reflects the slight upward arch that forms before the plate begins its downward bend. The ocean floor here rises subtly above the surrounding abyssal plain, creating a broad swell that stretches parallel to the trench. This rise is not formed by volcanic activity or sediment accumulation. Instead, it results from the mechanical response of the plate as it begins to curve under the forces, guiding it toward the subduction zone. Beyond the crest of the outer rise, the plate's shape changes more dramatically. The lithosphere bends downward toward the trench, forming a broad arc that leads into the deeper valley of the subduction boundary. As the rock curves, stresses develop within the upper layers of the plate. The outer surface of the bending lithosphere experiences tension as it stretches across the arc, while deeper layers compress beneath it. These opposing stresses create fractures that extend through the crust, forming networks of faults that slice across the seafloor. These bending-related faults often run roughly parallel to the trench, tracing the direction of the stresses generated by the flexing plate. Along these fractures, sections of the crust can shift slightly, adjusting to the curvature imposed by the approaching boundary. Some faults form long ridges and scarps that alter the texture of the ocean floor, while others remain subtle, hidden within the sediment that blankets parts of the plate. Together, they record the mechanical strain that develops as the lithosphere begins its descent toward the mantle. As the bending continues, the curvature of the plate helps shape the form of the trench itself. The depth and slope of the trench are influenced by how sharply the plate flexes as it approaches the boundary. A steeper bend can create a deeper, narrower depression in the seafloor, while a more gradual curve produces a broader transition between the abyssal plain and the trench. In this way, the geometry of the bending plate contributes directly to the contours of the trench that appears at the surface of the ocean floor. This flexure is not a single event frozen in time. The oceanic plate continues to move toward the boundary year after year, bringing new sections of crust into the region where bending begins. As each portion of the plate approaches the trench, it experiences the same gradual transformation, rising slightly at the outer rise before curving downward toward the subduction zone. The process unfolds continuously along the length of the boundary, renewing the pattern of bending as fresh lithosphere arrives. Through this steady motion, the seafloor near the trench remains part of an evolving structure rather than a static landscape. The bending of the plate, the formation of faults, and the slow adjustment of the crust all reflect the ongoing forces that guide the plate toward its descent into the mantle. Across immense spans of geological time, the ocean floor approaches the boundary, flexes under the weight of the sinking slab, and gradually joins the deeper movement shaping the structure of the trench. Far from the deep tectonic forces shaping the crust below, another quiet process unfolds through the slow movement of particles drifting through the ocean. Tiny fragments of rock, clay, and organic material travel vast distances through the water column before settling gently onto the seafloor. These grains begin their journey on distant continents, where mountains erode under wind and rain. Rivers gather the worn fragments and carry them steadily toward the sea, releasing their cargo into coastal waters where currents distribute the material across the ocean basin. Once in the open ocean, these sediments spread gradually across the abyssal plains. Some settle directly from the water column, descending slowly through the dark layers of the sea. Others are carried across the sea floor by bottom currents that creep along the ocean floor with patient persistence. Over time, these drifting particles accumulate in thin layers that blanket large areas of the deep ocean. In most regions, the accumulation proceeds quietly and evenly, forming a soft covering of sediment that grows thicker across the ages. Near deep ocean trenches, however, the behavior of these sediments becomes more dynamic. The steep slopes leading into the trench create pathways along which loose material can move downward. When sediment builds up along the upper edges of the trench walls, gravity can eventually pull portions of this material loose. Entire masses of sediment may begin to slide down the slopes, gathering speed as they descend toward the deeper parts of the trench. These movements often take the form of turbidity currents, dense flows of sediment-rich water that surge across the seafloor like underwater avalanches. Within these currents, suspended particles remain mixed within the moving water, allowing the flow to travel long distances through deep channels and across the trench floor. As the current slows, the sediment settles out in layered deposits that gradually reshape the bottom of the trench. Each event leaves behind a new blanket of material that adds to the complex layering of the deep basin. In other cases, the sediment moves through submarine landslides that occur along the steep walls of the trench. Portions of the slope collapse under their own weight, sending blocks of sediment and rock tumbling downward into the deeper valley. These slides may break apart as they descend, spreading their contents across the trench floor in uneven deposits. Over long periods, repeated landslides contribute additional layers of sediment that slowly accumulate within the deepest parts of the trench. At first glance, this steady supply of sediment might suggest that the trench should gradually fill and become shallower. In some areas, the trench floor does indeed gather thick sequences of deposited material that soften the contours of the basin, yet the geological forces shaping the trench continue to operate beneath these sediments. The bending and descent of the oceanic plate proceed regardless of the thin blankets of material resting upon its surface. As the lithosphere continues to sink along the subduction boundary, the structural depression of the trench can deepen even while sediments accumulate within it. Portions of the seafloor may move downward faster than sediment can fill the space above, preserving the extreme depth of the trench despite the steady rain of particles from above. In other regions, newly deposited sediment may later be carried downward along with the sinking plate, gradually entering the deeper geological cycle unfolding beneath the ocean floor. Through this balance of movement and accumulation, the trench becomes a place where opposing processes occur at the same time. Sediment arrives continuously from distant continents and ocean currents, settling across the deep basin in layers that record the passage of geological time. At the same time, the tectonic forces guiding the plate downward reshape the underlying structure of the seafloor. The result is a landscape that evolves through both quiet deposition and deep tectonic motion. The trench floor gathers the slow drift of sediments from across the Pacific, while beneath those layers, the lithosphere continues its descent toward the mantle. Over immense spans of time, the interplay between these processes allows the trench to deepen in some regions, even as new material settles into its depths, weaving together two gradual forces that shape the hidden contours of the ocean floor. Long before modern instruments could map the ocean floor in detail, the depths of the sea were approached with tools that relied on patience and gravity. Sailors lowered long lengths of rope or cable into the water, attaching heavy weights to the end so the line would sink straight through the vast column of seawater. When the weight finally touched the bottom, the length of the line offered a rough estimate of the ocean's depth. These early soundings required calm seas and careful measurement, yet even under ideal conditions, the results carried large uncertainties. Currents could drag the line sideways, the weight might sink into soft sediment, and the sheer scale of the ocean made precise measurement difficult. Despite these limitations, such weighted lines provided the first hints that some regions of the Pacific were far deeper than anyone had imagined. Expeditions crossing the western Pacific occasionally reported extraordinary depths when their cables descended farther than expected. Each sounding offered a glimpse into a hidden landscape far below the reach of sunlight, suggesting the presence of immense depressions within the ocean floor. These early measurements were imperfect, yet they laid the foundation for later attempts to understand the true depth of the planet's deepest waters. As technology advanced, scientists began to replace physical lines with sound. Ships equipped with echo-sounding instruments sent pulses of acoustic energy downward through the water. When these sound waves struck the seafloor, they reflected upward and returned to receivers mounted beneath the vessel. By measuring the time required for the signal to travel down and back, researchers could calculate the depth of the water beneath the ship. This method allowed far more efficient exploration of the ocean basin, since sound traveled rapidly through seawater and could probe depths far beyond the reach of cables. Echo sounding transformed the mapping of the ocean floor. As ships crossed the Pacific, continuous streams of depth measurements traced the contours of submerged ridges, plains, and trenches. The method revealed that the seafloor was not a featureless expanse, but a complex terrain shaped by geological processes unfolding beneath the waves. In regions near the Mariana Islands, echo-sounding profiles showed the seafloor dropping sharply into an enormous depression, confirming that the trench extended far deeper than surrounding areas of the Pacific Basin. Further improvements in acoustic technology eventually led to the development of multi-beam sonar systems. Instead of sending a single pulse directly beneath the vessel, these instruments project a wide fan of sound beams that spread outward across the seafloor. Each beam returns a depth measurement from a slightly different point on the ocean floor, allowing scientists to construct detailed maps of underwater terrain. As ships travel across the trench, thousands of measurements combine to create high-resolution bathymetric images that reveal slopes, ridges, and depressions hidden within the depths. Even with these powerful tools, mapping the deepest parts of the ocean remains challenging. The immense pressure and darkness of the deep sea limit direct observation, leaving acoustic methods as the primary means of exploration. Small variations in the speed of sound through seawater can influence the accuracy of measurements. Temperature, salinity, and pressure all affect how sound waves travel through the water column, requiring careful calibration to produce reliable depth estimates. Different research expeditions may also use slightly different equipment, processing techniques, and navigation systems. As a result, depth measurements recorded during separate surveys sometimes vary by several meters. These differences do not necessarily indicate errors. Instead, they reflect the complexity of measuring a landscape that lies miles beneath the surface of the ocean, where signals must travel through shifting layers of water before reaching the seafloor. Through the gradual refinement of these technologies, scientists have built increasingly detailed maps of the deepest parts of the Pacific. Each survey adds new layers of information, refining the understanding of the trench's structure and revealing subtle features within its vast depression. Yet the effort to measure the deepest point continues to unfold, guided by instruments that translate echoes from the dark ocean floor into the quiet contours of the hidden world below. When researchers map the seafloor of the deepest trenches, the numbers they record often appear precise to the meter. Yet, when the results of different expeditions are placed side by side, the values do not always align perfectly. Small variations emerge between surveys conducted years apart, even when the same region of the trench is examined. These differences do not arise from careless work or flawed instruments. They reflect the subtle challenges involved in measuring a landscape hidden beneath miles of moving seawater. The measurement begins with sound traveling through the ocean. Sonar systems send pulses of acoustic energy downward, waiting for the returning echo that marks the position of the seafloor. The calculation of depth depends on how quickly that sound wave moves through the water column. Although sound travels rapidly through seawater, its speed is not constant. Temperature, salinity, and pressure all influence how quickly acoustic waves move through the ocean. Warmer water allows sound to travel slightly faster, while colder water slows it down. Differences in salt concentration also affect the density of the water, altering the behavior of the sound wave as it passes through. In the deep ocean, these conditions can vary across layers of water stacked thousands of meters thick. Near the surface, sunlight warms the water and creates a relatively mixed layer influenced by winds and currents. Far below, colder and denser water masses form distinct layers that extend across vast regions of the ocean basin. As a sonar pulse travels downward through these layers, its speed changes subtly in response to the shifting temperature and salinity. Scientists measure these properties carefully during each survey, yet even small variations can influence the final calculation of depth by a few meters. Calibration of instruments adds another layer of complexity. Sonar systems must be tuned precisely to ensure that the timing of transmitted and received signals remains accurate. Minor differences in calibration between research vessels can lead to small discrepancies in measured depth. The equipment itself is capable of remarkable precision, but each expedition requires careful adjustment to account for local conditions in the ocean. The exact position of the survey vessel also plays a role in the final measurement. Modern mapping relies on satellite navigation to determine the location of a ship at sea. Although these systems provide extraordinary accuracy, slight variations in positioning can still influence how the seafloor is mapped. The deepest parts of the trench often consist of narrow depressions and uneven terrain. A small change in the ship's path across this complex landscape can produce slightly different depth readings depending on the precise location of each sonar beam. Once the acoustic data are collected, they must be processed into a coherent map of the seafloor. This stage involves filtering noise, correcting for water conditions, and combining thousands of individual measurements into a detailed model of the trench floor. Different research teams may apply slightly different processing techniques as they refine their maps. These methodological choices can influence the final interpretation of the deepest point within a surveyed region. Because of these factors, the recorded depth of the trench may vary slightly from one expedition to another. One survey might identify a particular depression as the lowest point, while a later survey with different equipment or processing methods may measure a nearby location as marginally deeper. The differences are often small, sometimes only a few meters, yet they illustrate how measuring the deepest parts of the ocean remains a delicate task. Over time, as mapping technology improves and more surveys are conducted, the understanding of the trench floor becomes clearer. Each expedition adds new detail to the growing portrait of the deep ocean landscape. The measured depth of the deepest point may shift slightly as this picture sharpens, reflecting the gradual refinement of knowledge about a place that lies far beyond direct human reach. At the farthest limits of ocean depth lies a place often imagined as a single, isolated point, the bottom of a vast vertical shaft descending into darkness. The name Challenger Deep sometimes carries that impression, as though the deepest place on Earth were a solitary hole carved neatly into the floor of the Pacific. The true shape of this region tells a quieter and more intricate story. Rather than a single pit, Challenger Deep forms part of a much broader depression within the larger structure of the Mariana Trench. The trench itself stretches across a long arc of the western Pacific, and within that sweeping valley, the deepest region appears as a complex landscape of smaller basins and ridges. Challenger Deep occupies one of these internal depressions, a portion of the trench where the seafloor reaches its greatest known depth. When mapped in detail, the area reveals a series of subbasins arranged along the floor of the trench, rather than a single smooth cavity. Each basin holds its own variations in depth and contour, shaped by the geological forces acting along the boundary between tectonic plates. These subbasins lie relatively close to one another, yet their depths differ by several meters or more across short distances. Some sections descend slightly farther than neighboring areas, while others rise gently into low ridges that separate the basins from one another. The terrain of the trench floor therefore resembles a broad valley containing smaller hollows and subtle rises rather than a perfectly symmetrical depression. These variations reflect the complex stresses acting within the bending crust of the subduction zone. The lithosphere beneath Challenger Deep continues to respond to forces originating far below the seafloor. As the oceanic plate bends and descends into the mantle, the surface above adjusts gradually to those movements. The crust can fracture along faults, shift slightly along boundaries, and settle unevenly as sediments accumulate across the basin. Each of these processes contributes to the irregular shape of the trench floor, creating subtle differences in depth from one part of Challenger Deep to another. Because of this complexity, determining the exact lowest point within the region requires careful mapping. High-resolution sonar surveys reveal slopes that tilt gently across the floor of the depression. Within these slopes, certain pockets extend slightly deeper than surrounding areas. These pockets define the places where measurements often identify the greatest depth. Yet even within the deepest basin, the seafloor does not form a perfect bottom. Instead, it spreads across a landscape where depth varies across short distances, shaped by the gradual motion of the surrounding crust. Sediment settling through the water column also contributes to the evolving structure of the basin. Fine particles drifting downward accumulate along the trench floor, forming soft layers that conform to the contours of the underlying rock. In some places, these sediments gather more thickly, smoothing small irregularities, while in other areas, the underlying geology remains more clearly expressed. The combination of tectonic motion and sediment deposition gradually alters the shape of the basin across geological time. The presence of several sub-basins within Challenger Deep reveals how the deepest part of the ocean forms within an active tectonic environment rather than a static cavity. The bending of the descending plate, the slow shifting of faults, and the quiet settling of sediments all contribute to the evolving form of the trench floor. Each process leaves subtle marks upon the landscape, shaping a terrain far more intricate than a single hole in the seabed. Viewed through detailed maps and acoustic surveys, Challenger Deep emerges as a broad depression composed of interconnected basins nestled within the larger trench system. Its deepest points lie within this complex terrain where the ocean floor reaches extraordinary depths before rising again toward the surrounding slopes. The region stands as a reminder that even the most extreme features of the planet often possess layered structures and quiet variations, reflecting the continuous geological activity shaping the hidden floor of the deep ocean. Far below the drifting layers of the ocean, weight gathers in silence. Each meter of descending water adds its own small share of pressure, and over miles of depth, those increments accumulate into an immense force pressing steadily upon the seafloor. By the time the deepest basins of the trench are reached, the water above forms a towering column whose mass bears down with extraordinary intensity. The pressure at these depths exceeds 16,000 pounds per square inch, a force far beyond the conditions found anywhere on land. This pressure comes not from sudden impacts or violent compression, but from the quiet persistence of gravity acting on the ocean itself. Every molecule of seawater above the trench contributes to the load. The deeper the water becomes, the greater the number of layers pressing downward. At the deepest points of the ocean, the weight of this column creates an environment where the surrounding rocks and sediments exist under a constant, unrelenting squeeze. Under such conditions, materials behave differently than they do near the surface. Rocks that might fracture easily in shallower environments can respond more gradually when subjected to extreme pressure. Instead of breaking abruptly, Some minerals adjust their internal structure to accommodate the stress. The atoms within the crystal lattices shift slightly closer together, allowing the rock to withstand the enormous load pressing in from all directions. Sediments, resting along the trench floor, experience this pressure in another way. As layers of fine particles accumulate over time, the weight of the water and the material above compresses the grains more tightly together. Pores that once held small pockets of seawater slowly shrink as the particles settle into a denser arrangement. This process, known as compaction, transforms loose sediment into more solid layers of rock over geological time. Each new deposit of material increases the pressure on the layers below, gradually strengthening the structure of the seafloor. Even solid crust responds subtly to the immense load imposed by the ocean above. The lithosphere beneath the deepest basins remains under constant compression, which influences how faults move and how fractures propagate through the rock. When stress accumulates within the crust, the surrounding pressure can affect the manner in which the rock yields. Instead of producing wide-open fractures, the rock may shift along tighter fault planes, where surfaces remain pressed firmly together by the weight of the overlying water and sediment. The crushing pressure of the deep ocean also influences the shape of the trench floor itself. Slopes that might collapse easily in shallow environments can remain stable under greater compression. The immense load pressing downward increases the friction between grains of sediment and fragments of rock, helping maintain steep walls within the deepest sections of the trench. At the same time, pressure encourages the gradual compaction of materials that gather along the basin floor, subtly altering the contours of the landscape over long periods. Within this environment, the boundary between rock and sediment becomes part of a tightly compressed system shaped by both tectonic forces and the weight of the ocean above. As the underlying crust bends and shifts along the subduction boundary, the pressure from the water column influences how the surface materials respond to those deeper movements. Layers settle, faults adjust, and sediments slowly compress, while the immense load of the ocean continues to bear down from above. The result is a geological setting where pressure quietly governs the behavior of matter. The rocks beneath the trench endure the constant squeeze of the water column, while tectonic forces guide the slow motion of the crust below. Together, these influences create conditions unlike those found anywhere else on the planet's surface, shaping the deepest parts of the ocean floor under the steady weight of the sea. Beneath the descending edge of the oceanic plate lies a region of the planet that remains hidden from direct observation. Far below the seafloor, beyond the deepest fractures of the crust, the descending slab enters the upper mantle. This vast layer of Earth extends thousands of kilometers downward and forms the slowly flowing foundation beneath the rigid plates of the lithosphere. Though solid in composition, the mantle behaves over long periods like an extremely thick fluid, capable of gradual movement under the influence of heat and pressure. As the oceanic plate sinks into this environment, it carries with it minerals that formed at the surface of the Earth millions of years earlier. The slab remains colder than the surrounding mantle rock because it spent immense spans of time exposed to the cooling influence of the ocean above. This contrast in temperature plays an important role in the interaction between the descending plate and the mantle that surrounds it. The colder slab moves through a hotter environment, creating a boundary where thermal and chemical changes unfold slowly over time. Within the upper mantle, temperatures rise steadily with depth. Rock that appears rigid at the surface gradually becomes more capable of slow deformation under these increasing temperatures and pressures. The descending slab, still relatively cool and dense, continues its downward motion through this warmer mantle material. As it sinks deeper, pressure compresses the minerals within the slab, while heat from the surrounding mantle begins to influence their structure. One of the most significant changes occurs when water contained within the minerals of the slab is released into the surrounding mantle. Oceanic crust and sediments often carry water locked within the structure of their minerals. As the slab descends and experiences higher temperatures and pressures, chemical reactions begin to break down those minerals. The water once trapped within them escapes into the mantle above the sinking plate. The presence of this water alters the behavior of the surrounding mantle rock. In dry conditions, mantle rock requires extremely high temperatures before it begins to melt. When water is introduced into the system, the melting temperature of the rock decreases. Portions of the mantle above the descending slab may therefore begin to melt partially, producing small amounts of molten material that rise slowly through the surrounding rock. These pockets of melt do not form vast, underground lakes of magma. Instead, they appear as scattered regions where small fractions of rock transition into molten form within the solid mantle. The melt is less dense than the surrounding material, allowing it to migrate upward through fractures and porous pathways within the overlying crust. Over long spans of time, these rising melts can contribute to volcanic systems that develop on the overriding plate above the subduction zone. While these processes occur far beneath the ocean floor, their influence gradually extends upward through the structure of the crust. The release of fluids, the formation of partial melts, and the flow of mantle material all contribute to the forces acting along the boundary between plates. These deep interactions help shape the mechanical behavior of the lithosphere above, affecting how the crust bends, fractures, and adjusts along the trench. The mantle beneath the trench therefore acts as more than a passive backdrop to the movement of tectonic plates. It participates actively in the transformation of descending crust, guiding the chemical and thermal changes that accompany subduction. The sinking slab, the circulating mantle, and the gradual rise of melt together form a system that connects the deepest interior processes of the Earth with the structure of the seafloor above. Through this hidden interaction, the deep mantle quietly influences the evolving landscape of the trench. Forces generated far below the ocean floor travel upward through the lithosphere, shaping the form of the boundary where the oceanic plate bends and descends. The surface features of the trench reflect these deeper processes, revealing how the interior of the planet continues to shape the structure of the seafloor from far beneath the waves. Across the surface of the planet, the crust does not rest upon an immovable foundation. Beneath it lies the mantle, a vast layer of slowly deforming rock that allows the rigid plates above to maintain a delicate balance. This relationship between crust and mantle can be imagined as a form of geological buoyancy. The lithosphere, composed of crust and the uppermost mantle, behaves like a massive raft floating upon deeper material that can flow gradually under pressure. The balance between these layers follows a principle known as isostacy, a quiet equilibrium that shapes the vertical position of Earth's surface. Within this system, the height or depth of any region depends on the distribution of mass above and below the mantle boundary. Thick sections of crust press deeper into the mantle, while thinner or denser areas sink lower within this slow-moving foundation. The mantle responds by adjusting beneath the weight of the overlying rock, allowing the surface to maintain a state of balance over geological time. These adjustments do not occur quickly. Instead, they unfold slowly as the mantle yields to the pressure of the plates resting above it. In regions surrounding deep ocean trenches, this balance becomes especially complex. The descending oceanic plate introduces a large mass of dense rock into the mantle as it sinks along the subduction boundary. As the slab moves downward, it redistributes mass within the deeper layers of the Earth. This redistribution alters the forces acting on the lithosphere near the trench, influencing how the surrounding crust adjusts vertically. When mass shifts within the Earth, the crust responds by seeking a new equilibrium. Portions of the lithosphere may settle slightly as weight increases beneath them, while other areas may rise gradually as pressure is relieved. These movements form part of the ongoing isostatic adjustment occurring along tectonic boundaries. Although the vertical changes are often subtle, they accumulate across immense spans of time as the balance between crust and mantle evolves. The sinking slab beneath a trench contributes directly to this process. As the plate descends, it draws mass downward into the mantle, changing the distribution of material within the deeper layers of the planet. The surrounding lithosphere adjusts slowly in response to this shift. In some areas near the boundary, the crust may flex downward as the descending slab pulls on the plate above. In other areas, the redistribution of mass can allow neighboring regions to rise slightly as the mantle flows to accommodate the changing load. These vertical adjustments occur gradually because the mantle behaves neither as a rigid solid nor as a freely flowing liquid. Instead, it moves slowly under sustained pressure, allowing the lithosphere above to settle into new positions over long periods. The process resembles a vast and patient balancing act, where the crust continually adjusts to the changing distribution of mass beneath it. Sediment accumulation, tectonic motion, and the descent of dense slabs all contribute to this evolving balance. Each change in mass alters the pressure exerted upon the mantle, encouraging subtle movements that bring the system closer to equilibrium. Over millions of years, these adjustments can influence the depth of ocean basins and the elevation of nearby regions of crust. Near the Mariana Trench, the interplay between sinking plates and mantle response forms part of this quiet adjustment. As the descending slab carries dense rock downward, the surrounding lithosphere continues to respond to the shifting balance below. The trench itself reflects not only the bending of the plate, but also the deeper adjustments occurring within the mantle beneath it. Through the slow mechanism of isostacy, the surface of the planet remains connected to movements unfolding far below. The crust floats upon the mantle in a state of continual balance, rising or settling as the distribution of mass changes within the Earth. Over immense spans of time, this patient process allows the surface of the planet to adjust gradually, while the deeper layers continue their steady transformation. Along the margins where tectonic plates converge, the boundary between them does not remain perfectly clean or sharply defined. The descending plate moves beneath its neighbor with immense force, and along that interface, the crust of the overriding plate can slowly lose pieces of itself. Rock that once formed part of the stable edge of the upper plate may gradually be removed, carried downward into the subduction zone as the plates continue their long interaction. This quiet process is known as subduction erosion, and it unfolds slowly along the deep boundaries of the ocean trenches. As the oceanic plate slides beneath the edge of the overriding plate, the contact between them becomes a region of intense mechanical interaction. The surface of the descending plate is rarely smooth. It carries ridges, rough volcanic features, and thick accumulations of sediment that formed during its long journey across the ocean basin. When these irregular surfaces reach the boundary between plates, they press against the underside of the overriding crust. The result is a gradual scraping effect that can loosen fragments of rock from the base of the upper plate. These fragments may break away in pieces ranging from small blocks to large sections of crust. Once detached, they are drawn downward with the descending slab, becoming part of the material that enters the mantle along the subduction boundary. This removal of crustal fragments gradually thins the edge of the overriding plate, altering the structure of the boundary over long spans of geological time. Unlike the sudden collapse of a cliff or landslide along a steep slope, subduction erosion occurs slowly and continuously. Each interaction between the descending plate and the base of the overriding crust removes only small amounts of material. Yet, as the plates continue to move year after year, these small losses accumulate. Over millions of years, entire layers of rock can be stripped from the underside of the plate above the trench. The erosion is not limited to the direct contact between the plates. As the descending slab pulls downward, it can also create conditions that destabilize nearby portions of the crust. Faults may develop along the edge of the overriding plate, allowing sections of rock to shift gradually toward the trench. These weakened regions become more susceptible to removal as the boundary continues its slow motion. Through this steady loss of material, the structure of the trench itself can change subtly. When fragments of the overriding plate are removed and carried downward, the edge of the plate may settle slightly toward the subduction boundary. This adjustment can influence the slope of the trench walls and the overall shape of the basin. Over geological time, the combined effects of bending, sediment movement, and subduction erosion contribute to the evolving form of the trench. Evidence of this process appears in geological records preserved along many subduction zones. Studies of rock formations within volcanic arcs and nearby regions reveal that sections of crust have been removed from the edges of plates over millions of years. These missing portions of crust are thought to have descended along with the subducting slab, becoming part of the deeper mantle. In the region of the Mariana Trench, similar processes are believed to occur along the boundary where the Pacific Plate descends beneath the Philippine Sea Plate. The interaction between these massive plates allows fragments of the overriding crust to be gradually stripped away and carried downward into the interior of the Earth. Each small loss contributes to the long-term evolution of the trench boundary. Through this slow and persistent form of erosion, the subduction zone reshapes itself from below as well as from above. Material that once formed part of the edge of the overriding plate disappears into the depths along with the descending slab. Over immense spans of time, this quiet removal of rock alters the structure of the trench, revealing how even the deepest features of the ocean floor continue to evolve through the patient forces of plate motion. Long before the descending plate disappears into the deeper mantle, seawater begins a quiet journey into the crust itself. The ocean floor is not perfectly sealed stone. Over time, it develops networks of fractures formed by cooling, tectonic stresses, and the gradual bending of the plate as it approaches a subduction boundary. These cracks allow seawater to seep slowly downward, penetrating the upper layers of the oceanic crust and reaching rocks that once formed deep within the Earth's interior. The water does not simply fill empty spaces. As it travels through the fractured crust, it encounters minerals that formed under high temperatures within ancient volcanic rock. When seawater interacts with these minerals, chemical reactions begin to alter the structure of the rock itself. At elevated temperatures and pressures, the water reacts with minerals such as olivine and pyroxene, transforming them into new mineral forms that contain water within their crystalline structures. One of the most important of these transformations is known as serpentinization. During this process, minerals within the mantle-derived rock react with water and reorganize into serpentine minerals. These new minerals incorporate water into their structure and expand slightly as they form. The rock becomes chemically and physically different from the material that existed before the reaction began. The transformation proceeds gradually as long as water continues to circulate through the fractured crust. As the plate continues its slow descent toward the trench, the altered rock carries this stored water deeper into the earth. With increasing depth, temperatures rise and pressures intensify. Under these changing conditions, the minerals that formed during serpentinization eventually begin to break down. When they do, the water once locked inside their crystal structures is released again, returning to a fluid state within the surrounding rock. The release of this fluid influences the physical behavior of the crust and mantle near the subduction boundary. Water acts as a powerful agent that can reduce the strength of rock under certain conditions. When fluids move through fractures and grain boundaries, they can weaken the bonds between mineral grains. This weakening allows the rock to deform more easily under the immense forces generated by plate motion. As a result, sections of the subduction zone may become more susceptible to slow deformation. Rock that might otherwise resist movement can begin to bend, slide, or flow more gradually when fluids are present within its structure. These changes occur far beneath the ocean floor, hidden within the deep environment where the descending slab meets the surrounding mantle. The movement of fluids also influences chemical processes within the mantle above the sinking plate. As water migrates upward through cracks and porous pathways, it alters the composition of the surrounding rocks. These changes can contribute to melting processes that generate small volumes of magma deep beneath the crust. Although the effects are subtle and unfold over immense spans of time, they form part of the complex interaction between water, rock, and heat within subduction zones. Hydrothermal activity, therefore, connects the surface of the ocean with deep geological transformations unfolding within the earth. Water that once circulated freely through the ocean basin becomes part of a hidden cycle, traveling downward into the crust through fractures before being carried deeper by the descending plate. Chemical reactions reshape the minerals it encounters, storing and later releasing the fluid as conditions change with increasing depth. Through this quiet exchange between water and rock, the structure of the subduction zone gradually evolves. Minerals transform, fluids migrate through the crust, and sections of rock become more flexible under pressure. These processes occur far from direct observation, yet they play an important role in shaping how the descending plate behaves as it continues its journey beneath the ocean floor. Over geological time, the interaction between seawater and the sinking crust contributes to the slow transformation of the boundary between plates. Beneath the immense weight of the ocean and the pressures of the mantle below, hydrothermal processes quietly alter the strength and composition of the rocks that guide the descent of the lithosphere into the interior of the planet. Deep within the boundary where the oceanic plate bends and descends, the rocks of the Earth begin to behave in ways that differ from the rigid surfaces familiar at the planet's exterior. At great depths, pressure and temperature quietly transform the mechanical character of the crust and mantle. Materials that would fracture abruptly near the surface can instead move gradually when subjected to the immense forces present far below the ocean floor. The movement is not fast or violent. It unfolds slowly, almost imperceptibly, as the rock adjusts to the stresses acting upon it. This behavior is known as plastic deformation. Unlike brittle deformation, where rock breaks suddenly along fractures, plastic deformation allows rock to change shape without forming large cracks. Under the intense pressure found deep within subduction zones, mineral grains inside the rock shift slightly relative to one another. The crystal structures within the minerals may rearrange themselves, allowing the rock mass to bend and stretch without shattering. Over long periods, these microscopic adjustments permit the entire body of rock to flow gradually. The difference between brittle and plastic behavior depends largely on depth and temperature. Near the surface, the crust remains relatively cool and experiences lower pressure. Under those conditions, rocks tend to fracture when stressed, producing faults and earthquakes that release accumulated strain. Deeper within the earth, the increasing heat and pressure create an environment where the minerals within the rock become more capable of slow internal movement. Instead of snapping under stress, the rock deforms steadily, absorbing the forces applied to it. Within the descending plate beneath the trench, both types of behavior occur in different layers. The uppermost portions of the crust may still fracture occasionally, producing seismic events that release stored strain. Beneath these brittle zones, however, the deeper sections of the slab experience conditions that favor plastic deformation. Here the rock bends gradually as it continues its descent into the mantle. The motion is measured not in sudden shifts, but in slow changes that accumulate over thousands or millions of years. This slow movement is sometimes described as creep. In geological terms, creep refers to the gradual deformation of rock under constant stress. Within subduction zones, the immense weight of overlying rock and the forces generated by plate motion create persistent pressure that encourages this slow adjustment. The rock does not remain perfectly rigid under such conditions. Instead, it responds by flowing very slowly, allowing the structure of the descending slab to adapt to the stresses surrounding it. As the slab bends deeper into the mantle, plastic deformation helps distribute the stress across a broader region of rock. Instead of concentrating strain along a single fracture, the stress spreads through the surrounding material. This process reduces the likelihood of large, brittle breaks at those depths while allowing the plate to continue its downward journey. The bending of the slab therefore occurs through a combination of mechanisms, including occasional earthquakes in brittle layers and continuous creep within deeper plastic zones. The presence of plastic deformation also explains why motion within subduction zones never fully stops between seismic events. Even during long intervals without earthquakes, the rocks within the deeper portions of the boundary continue to adjust slowly. Mineral grains shift, crystal structures realign, and the slab gradually changes shape as it responds to the forces acting upon it. This steady movement ensures that the process of subduction continues uninterrupted through time. Across immense geological spans, these subtle adjustments contribute to the evolving structure of the trench and the surrounding crust. The descending slab bends, stretches, and flows as it sinks, guided by the combined influence of pressure, temperature, and gravity. The rock beneath the ocean floor therefore behaves not as a static framework, but as a dynamic system, capable of both sudden fracture and slow transformation. Through the quiet mechanism of creep and plastic deformation, the deeper parts of the subduction zone remain in constant motion. Even in the absence of earthquakes, the rocks continue their gradual adjustment beneath the immense weight of the ocean and the shifting plates above, shaping the hidden architecture of the trench far below the surface of the sea. Far beneath the seafloor, temperature rises gradually with depth, shaping the behavior of rock in ways that remain invisible from the surface. The increase is steady rather than dramatic, guided by the internal heat of the planet that has persisted since Earth first formed. As the crust descends toward deeper layers, the surrounding environment grows warmer, creating conditions that influence how the lithosphere bends, fractures, and flows along subduction boundaries. Within the uppermost layers of the crust, rocks remain relatively cool and rigid. Under these cooler conditions, they tend to resist deformation until stress becomes great enough to break them. This brittle response produces fractures and faults that sometimes release stored strain through earthquakes. As depth increases, however, the rising temperature begins to alter the internal structure of the minerals composing the rock. Heat gives atoms within crystal lattices greater freedom to shift slightly under pressure, allowing the rock to deform without immediately breaking. This gradual change in mechanical behavior means that rock strength does not remain constant as the plate descends into the mantle. In cooler regions near the surface, the crust behaves as a rigid shell, capable of storing large amounts of elastic strain. Deeper within the subduction zone, warmer conditions soften the rock, making it more capable of slow deformation. The lithosphere, therefore, transitions from a brittle outer layer to a deeper region where plastic behavior becomes more common. Temperature also affects the physical dimensions of rock through the process of thermal expansion and contraction. As materials warm, their atomic structures tend to expand slightly, increasing the volume of the rock. When temperatures decrease, those structures contract again. These subtle changes may appear small at the scale of individual minerals, yet across vast regions of the crust, they contribute to the long-term adjustment of geological structures. Variations in temperature can therefore influence how stresses accumulate and redistribute within the lithosphere. Beneath ocean trenches, heat flow varies from place to place depending on the movement of tectonic plates and the circulation of fluids within the crust. The descending plate carries relatively cool rock into deeper regions of the mantle, creating a temperature contrast between the slab and the surrounding material. This contrast affects the transfer of heat through the subduction zone, producing complex patterns of warming and cooling that extend through the crust and upper mantle. In some regions near the trench, the cold slab suppresses heat flow from the mantle below, maintaining lower temperatures within the surrounding rocks. In other areas, fluids released from the descending plate carry heat upward through fractures and porous pathways. These variations in thermal conditions influence the behavior of rocks within the boundary between plates, affecting how they bend and deform under the forces of tectonic motion. Over long spans of geological time, temperature changes contribute to the gradual transformation of minerals within the subducting plate. As the slab sinks deeper, the rising heat alters the stability of the minerals that formed in cooler environments near the surface. Some minerals break down and reorganize into new forms that are stable under higher temperatures and pressures. These transformations release fluids and modify the density of the rock, influencing the forces acting on the descending slab. Through these processes, temperature becomes an essential factor in the evolution of subduction zones. Heat governs how rocks respond to stress, how minerals transform at depth, and how fluids circulate within the crust. The thermal structure of the subduction boundary therefore shapes the mechanical behavior of the plates as they continue their slow movement beneath the ocean floor. Across immense stretches of time, the gradual increase of temperature with depth influences every stage of the plate's descent. Rock strength evolves, minerals transform, and the balance of forces within the trench adjusts quietly in response to the heat rising from the planet's interior. The slow warmth of the Earth thus becomes part of the hidden framework, guiding the long transformation of the deepest regions of the ocean floor. Across the Pacific Ocean, the seafloor is marked by long arcs where tectonic plates converge and descend into the mantle. These arcs form deep trenches that trace the edges of shifting plates, each shaped by the particular conditions of the boundary beneath it. Although the Mariana Trench is widely known as the deepest of these features, it is not the only place where the ocean floor drops dramatically toward the planet's interior. Other trenches extend across the Pacific Basin, each revealing a slightly different expression of the same underlying process. To the south of the Mariana region lies the Tonga Trench, another immense depression formed where the Pacific Plate moves beneath the smaller Tonga Plate. The Tonga Trench stretches along a narrow arc near the islands of Tonga and is among the deepest ocean trenches outside the Mariana System. In several locations along its length, the seafloor descends to extraordinary depths that approach those found in the deepest parts of the Pacific. The trench also displays steep walls and a sharply defined floor, reflecting the rapid motion of the plates along this boundary. Farther north and west, another subduction boundary forms the Philippine Trench. This trench lies along the eastern edge of the Philippine archipelago and marks the boundary where the Philippine sea plate interacts with neighboring plates. Although it does not reach the same extreme depths as the Mariana or Tonga trenches, it still forms a profound valley along the ocean floor. The structure of the Philippine Trench reveals a different combination of tectonic forces, including variations in plate motion and crustal composition that influence how the boundary develops. South of the Tonga region, the Kermadec Trench extends along another arc of the Pacific Basin. This trench follows the boundary where the Pacific Plate descends beneath the Australian Plate near the islands of New Zealand. The Kermadec system forms a long chain of deep depressions that resemble the structure of other subduction zones, yet maintain their own unique geometry. Some portions of the trench descend to great depths, while other sections appear slightly shallower, depending on the characteristics of the descending plate and the structure of the overriding crust. These differences among trenches arise from several factors that influence how subduction zones evolve. One important element is the age and density of the descending plate. Older oceanic crust tends to be colder and denser than younger crust, making it more likely to sink steeply into the mantle. When a plate descends at a steeper angle, the bending of the lithosphere near the boundary can produce a deeper trench along the ocean floor. The rate at which plates move toward one another also plays a role in shaping the depth and structure of trenches. Faster convergence can intensify the forces acting along the boundary, influencing how the descending slab bends and how the overriding plate responds to that motion. Over long spans of geological time, these differences in plate motion can produce variations in the depth and shape of trenches across the Pacific. Sediment supply offers another factor that distinguishes one trench from another. In regions where large amounts of sediment accumulate along the trench floor, deposits can partially fill the basin and reduce the measured depth of the seafloor. In other areas where sediment supply is limited, the trench may remain more sharply defined and deeper relative to its surroundings. Through these combined influences, each trench develops its own geological character. The Mariana Trench stands as the deepest example of this process, shaped by the interaction of dense oceanic crust, active plate motion, and the long history of subduction along its boundary. Other trenches share the same fundamental origin, yet display different depths and contours depending on the forces acting beneath them. Across the Pacific Basin, these great trenches reveal the diversity of structures created by converging plates. Each one represents a place where the surface of the Earth bends toward the mantle below, forming a deep valley along the ocean floor that reflects the unique balance of forces shaping that boundary through geological time. Over the immense spans of geological time, The surface of the planet rarely remains fixed in any single form. Boundaries between tectonic plates shift gradually, adjusting to the forces that move the crust across the mantle. In regions where one plate descends beneath another, this motion continues long after a trench first forms. The plates do not pause once the initial depression appears in the ocean floor. Instead, they continue their slow convergence, guiding the structure of the trench through an extended process of change. Where the Pacific Plate approaches the boundary near the Mariana region, the movement of the plate remains ongoing. Year after year, the plate advances toward the subduction zone, carrying new sections of oceanic lithosphere toward the place where the crust bends downward into the mantle. Each portion of the plate eventually reaches the boundary, joining the long sequence of rock that has already begun its descent. This persistent motion means that the forces shaping the trench remain active even today. Over human timescales, these movements are too small to produce dramatic alterations in the depth of the trench. The seafloor does not suddenly sink by large distances within a few generations. Yet, when the same motion continues across millions of years, the accumulated effect becomes far more significant. The lithosphere bends gradually as it approaches the boundary, and the ongoing descent of the slab can slowly modify the shape of the trench over geological intervals. Scientists study these processes using models that simulate the long-term evolution of subduction zones. By examining the behavior of descending plates under different conditions, researchers can estimate how trenches may change as plates continue to converge. These models consider factors such as the density of the slab, the temperature of the surrounding mantle, and the rate at which plates move toward one another. Together, these elements influence how deeply the plate bends before it descends and how the trench floor responds to that motion. Certain conditions allow trenches to deepen gradually over time. When the descending plate is relatively old and dense, it tends to sink more readily into the mantle. The greater weight of the slab encourages a steeper angle of descent, which can enhance the curvature of the plate near the boundary. This sharper bending may produce a deeper depression along the seafloor as the lithosphere folds downward into the subduction zone. The motion of the overriding plate also plays a role in this evolution. If the upper plate moves in a way that accommodates the downward bending of the slab, the trench may maintain a steep profile over long periods. In such settings, the structural depression along the boundary can persist or even deepen gradually as new sections of lithosphere arrive and begin their descent. Despite these possibilities, the depth of a trench cannot increase indefinitely. The mantle surrounding the descending slab provides resistance that limits how sharply the plate can bend. As the slab sinks deeper, the forces within the mantle gradually oppose further downward curvature. The mechanical strength of the lithosphere and the viscosity of the mantle together establish boundaries on how far the trench structure can deepen. Sediment accumulation and structural adjustments within the crust also influence the long-term depth of the trench. Material carried into the basin may partially fill sections of the trench floor, while tectonic adjustments along the boundary redistribute stresses within the surrounding plates. These processes interact with the downward bending of the lithosphere, producing a balance between forces that deepen the trench and those that modify its shape. Through this interplay of motion, resistance, and geological time, the trench continues to evolve gradually. The plates converge, the slab descends, and the surrounding mantle responds to the shifting mass within the Earth's interior. Over millions of years, these quiet adjustments shape the contours of the deepest parts of the ocean floor. The trench therefore exists not as a finished feature, but as part of an ongoing tectonic system. Its depth, reflects the balance of forces acting within the planet, a balance that continues to adjust as the plates move steadily across the surface of the Earth. Along the margins where tectonic plates meet, the shape of the ocean floor is never entirely fixed. The trenches that mark these boundaries appear immense and stable when viewed on human timescales, yet their structure evolves slowly under the influence of many interacting forces. While the motion of descending plates can deepen these depressions, other processes act quietly in the opposite direction. Over geological time, these influences may reduce the depth of a trench, altering the form of the boundary that once carved so sharply into the seafloor. One of the most gradual influences comes from the continuous arrival of sediment, material carried by rivers, ocean currents, and submarine flows eventually settles along the floor and slopes of deep trenches. Grain by grain, layers accumulate within the basin, softening the contours of the underlying rock. In regions where sediment supply is abundant, these deposits may grow thick enough to partially fill sections of the trench floor. The process unfolds slowly, often requiring millions of years before noticeable changes appear in the depth of the basin. The shape of the trench can also change through tectonic uplift, occurring along the edge of the overriding plate. Forces within the crust sometimes cause sections of rock near the boundary to rise gradually relative to the surrounding seafloor. This uplift may occur as stresses shift within the plate or as deeper structures adjust to the evolving geometry of subduction. When uplift affects the slopes or floor of the trench, portions of the basin may become slightly shallower than they were in earlier stages of the boundary's history. Large-scale changes in plate motion can produce even more significant adjustments. Tectonic plates do not always move along the same paths indefinitely. Over immense spans of time, the direction and rate of plate motion can reorganize as new boundaries form and older ones weaken. When this type of tectonic reorganization occurs, the forces driving subduction along a trench may diminish or change direction. If convergence slows or ceases, the trench may gradually lose the conditions that originally maintained its depth. Another process capable of altering the structure of a trench involves the deeper portion of the descending slab itself. As the slab sinks into the mantle, stresses within the rock can eventually cause sections of the slab to detach from the portion of the plate still connected to the surface. This event, known as slab breakoff, separates the deeper segment of the plate from the shallower portion that once guided its descent. When this separation occurs, the forces pulling the slab downward are reduced, allowing the structure of the boundary above to adjust. Without the strong downward pull of the sinking slab, the lithosphere near the trench may gradually respond by relaxing upward. The crust can flex slowly as the balance of forces beneath it changes. Although these adjustments unfold gradually, they can influence the long-term shape of the trench, allowing portions of the basin to become less deep than they were when the slab remained fully attached. Through these combined influences, trenches reveal themselves as dynamic features shaped by multiple geological processes. Sediment accumulation softens the basin floor. Tectonic uplift alters the elevation of surrounding crust, and deeper changes within the mantle modify the forces acting on the descending plate. None of these processes operate quickly, yet across the vast scale of geological time, they contribute to the steady transformation of the trench. The Mariana Trench, like other subduction boundaries across the Pacific, exists within this balance of forces. Its present depth reflects the current interaction between descending lithosphere, sediment deposition, and the evolving structure of the surrounding plates. As those conditions continue to change through time, the trench will adjust accordingly, reflecting the shifting equilibrium of Earth's tectonic system. Seen through this longer perspective, a trench is not a permanent excavation within the seafloor. It is a momentary expression of deeper forces moving within the planet, a structure that can deepen, soften, or transform as the tectonic environment around it continues its slow evolution. Long before the present arrangement of oceans and continents took shape, the region that would eventually hold the Mariana Trench belonged to a very different geological landscape. The Pacific Basin itself has existed for tens of millions of years, and the boundary that now forms the trench developed gradually within that wider history of plate motion. The trench did not appear suddenly as a fully formed depression in the seafloor. Instead, it emerged slowly as tectonic forces reorganized the edges of the Pacific Plate and neighboring plates within the Western Pacific. Geological evidence suggests that subduction along this boundary began roughly 50 million years ago. At that time, shifting plate motions created conditions that allowed the Pacific Plate to begin descending beneath the plate, now known as the Philippine Sea Plate. As convergence continued, the lithosphere near the boundary started to bend downward, forming an early version of the trench. The depression at that stage would have been shallower than the modern trench, reflecting the early phases of the subduction process. Over millions of years, the descending slab continued its slow movement into the mantle. With each passing epoch, new sections of oceanic crust approached the boundary and joined the downward motion. The repeated bending of the lithosphere gradually deepened the structure along the edge of the plate. At the same time, adjustments within the surrounding mantle and crust allowed the trench to evolve into the elongated basin that exists today. Marine geological studies provide clues to this long transformation. Sediment cores collected from the surrounding seafloor preserve layers that record the changing conditions of the region over time. Within these layers, scientists find traces of volcanic ash, microscopic fossils, and mineral grains that reveal the history of ocean currents and tectonic activity in the area. By analyzing these deposits, researchers can reconstruct the environmental and geological conditions that accompanied the development of the trench. Seismic imaging techniques offer another window into the past. By sending sound waves deep into the crust and mantle, scientists can map the structure of the descending slab and the layers of rock surrounding it. These images reveal how the slab extends downward into the mantle, tracing a path that reflects millions of years of continuous subduction. The geometry of this slab provides evidence of the trench's long history, showing how the boundary has evolved as the plate continued its descent. Across geological time, the depth of the trench has likely changed in response to shifts in tectonic forces. Periods of faster plate convergence may have encouraged the lithosphere to bend more sharply, deepening portions of the basin. In other intervals, variations in sediment accumulation or changes in plate motion could have modified the contours of the trench floor. These adjustments occurred gradually, reflecting the slow rhythm of tectonic activity that shapes the surface of the Earth. The rocks beneath the Mariana region also record this extended timeline. Layers within the crust preserve evidence of volcanic activity associated with the subduction zone, including the formation of island arcs that developed above the descending slab. These volcanic chains mark stages in the evolving relationship between the Pacific Plate and the Philippine Sea Plate, each phase contributing to the geological narrative of the trench. Through these combined records, scientists have assembled a timeline that stretches across tens of millions of years. The Mariana Trench emerged during the early phases of subduction in the Western Pacific and deepened gradually as plate motion continued. Its present form reflects the cumulative result of countless small adjustments occurring over immense spans of time. Seen within this broader history, the trench becomes part of a much larger geological story. The The basin that now represents the deepest region of the ocean floor formed through a sequence of slow transformations driven by the motion of tectonic plates. Each layer of sediment, each shift in the descending slab, and each volcanic episode contributes another chapter to the long evolution of this remarkable feature of the Pacific seafloor. Far below the reach of sunlight, where the weight of the ocean presses steadily upon the seafloor, life persists in forms that seem almost improbable. The environment within the deepest parts of the trench presents conditions that differ profoundly from those at the surface of the ocean. Temperatures remain near freezing, pressure rises to extraordinary levels, and darkness is complete. Yet, within these depths, small communities of organisms continue their quiet existence, adapted to conditions that would challenge most other forms of life on the planet. Among the most remarkable inhabitants of these depths are microorganisms known as extremophiles. These microscopic organisms thrive in environments once thought too harsh to support life. In the sediments of the trench floor, microbial communities inhabit the tiny spaces between grains of mineral particles. There, they carry out chemical processes that allow them to survive in an environment lacking sunlight and subjected to immense pressure. Instead of relying on energy from photosynthesis, many of these microbes obtain energy through chemical reactions involving compounds dissolved in seawater or released from the surrounding rock. Within the soft sediments and scattered debris along the trench floor, small crustaceans known as amphipods also appear in surprising abundance. These creatures resemble tiny shrimp and move slowly across the seabed in search of organic material that drifts downward from the upper ocean. The trench acts as a natural collector for such material. Fragments of dead plankton, plant debris, and the remains of marine animals settle through the water column and eventually reach the bottom. Amphipods feed upon this detritus, forming part of a deep ecosystem that depends on resources arriving from far above. The survival of these organisms depends on biological adaptations that allow them to function under the immense pressure of the deep ocean. In most animals, high pressure would disrupt the structure of proteins and cellular membranes, interfering with the chemical reactions necessary for life. Species that inhabit the trench possess molecular structures that remain stable under these extreme conditions. Their cellular components contain specialized compounds that help maintain the proper shape of proteins and membranes despite the intense compression of the surrounding water. Some amphipods and other deep-sea animals also possess flexible bodies that respond gradually to pressure rather than resisting it. Their tissues contain relatively little rigid structure, allowing the organisms to tolerate the immense forces surrounding them. These biological strategies enable life to continue within an environment that might otherwise seem completely inhospitable. The presence of these organisms within the trench reflects the long continuity of life in the deep ocean, even as geological forces reshape the seafloor over time. The boundary between tectonic plates remains active beneath these ecosystems, and subtle adjustments in the crust can influence the distribution of habitats along the trench floor. Sediment slides, shifting slopes, and the slow bending of the lithosphere all alter the landscape in which these organisms live. Despite these changes, life adapts to the evolving structure of the trench. Microbial communities recolonize newly deposited sediments, and small animals move across the seafloor to exploit fresh sources of organic material. Over long intervals, the biological systems of the deep ocean adjust to the shifting environment created by tectonic processes. These ecosystems therefore exist in quiet partnership with the geological forces shaping the trench. While plates converge and slabs descend into the mantle, life continues within the sediments above, sustained by chemical energy and the slow arrival of nutrients from the ocean above. The organisms of the deep adapt to the gradual changes in their environment, maintaining a presence even as the structure of the seafloor evolves. Within the deepest reaches of the trench, biology and geology intersect in subtle ways. The organisms that inhabit this environment reveal how life can persist under extreme pressure and darkness, responding to conditions that change slowly across geological time, while the boundary between plates continues its patient transformation beneath the ocean floor. Long before cameras and robotic vehicles reached the deepest ocean basins, the floor of the trench remained an unseen frontier. Maps showed only an immense depression in the Pacific seafloor, measured by distant instruments but never directly witnessed by human eyes. The possibility of descending into that environment required technology capable of surviving pressures far beyond those encountered anywhere else on Earth. The first successful journey to the deepest known region of the ocean occurred in 1960 when the bathyscaphe Trieste began its slow descent toward the basin later known as Challenger Deep. Designed as a deep-sea research vessel, Trieste combined a steel pressure sphere with a large float filled with gasoline that provided buoyancy. Two explorers, Jacques Piccard and Don Walsh, entered the small spherical cabin and began a descent that would last several hours. As the vessel moved downward through the dark water column, pressure outside the craft increased steadily. The thick steel walls of the sphere protected the occupants from the surrounding forces, which grew immense as the depth increased. Eventually, the bathyscaphe reached the floor of the trench, more than 10,000 meters beneath the ocean surface. When the craft settled onto the seabed, the explorers observed fine sediments covering the bottom, stirred gently by the arrival of the vessel. Their brief stay confirmed that the deepest ocean basin was not an empty void, but a real landscape of soft deposits resting beneath the immense weight of the sea. For decades afterward, no other crewed descent returned to that depth. Advances in technology eventually renewed interest in exploring the deepest part of the ocean, leading to a new expedition many years later. In 2012, filmmaker and explorer James Cameron completed a solo descent to Challenger Deep using a specially designed submersible known as Deep Sea Challenger. Unlike the earlier bathyscaphe, this vessel was built with modern materials and advanced imaging equipment, allowing it to capture detailed observations of the seafloor. The journey followed a similar pattern of slow descent through the ocean's dark layers. As the submersible approached the deepest basin, the surrounding water pressure reached levels that tested the limits of engineering design. Cameron's craft contained a pressure-resistant cabin surrounded by flotation materials capable of withstanding the crushing forces of the deep ocean. Upon reaching the bottom, the submersible rested briefly on the soft sediment while cameras recorded the landscape of the trench floor. Images from the expedition revealed a broad plain of pale sediment extending across the deepest basin. The seafloor appeared relatively smooth in places, shaped by slow geological processes and the steady settling of fine particles from the ocean above. Small organisms moved across the sediment, confirming the presence of life even at these extreme depths. In the years since that expedition, modern exploration has increasingly relied on advanced submersibles and remotely operated vehicles. These machines allow scientists to study the deepest ocean regions with improved precision and safety. Some vehicles carry crews within reinforced pressure spheres, while others operate remotely, controlled from research vessels at the surface. Equipped with sonar systems, robotic arms, and high-resolution cameras, these vehicles can collect samples, map the terrain, and document the unique environment of the trench floor. Exploring such depths presents technical challenges that extend beyond pressure alone. Communication signals weaken through kilometers of water, making it difficult to maintain constant contact with vehicles operating near the seabed. Navigation also becomes complex in an environment where GPS signals cannot reach. Engineers rely on acoustic positioning systems and carefully calibrated instruments to determine the exact location of submersibles during their descent. Despite these challenges, each expedition provides new observations of the deepest parts of the ocean. The seafloor reveals a landscape shaped by geological forces yet softened by layers of sediment and inhabited by small organisms adapted to the surrounding environment. Human exploration has therefore transformed the trench from a distant measurement into a place that has been seen directly, confirming the remarkable conditions that exist at the deepest known point of the ocean floor. Long after the first explorers reached the trench floor, the work of understanding its full shape continues quietly across the Pacific. The deepest basins of the ocean are vast and remote, and even today large portions of the seafloor remain only partially mapped. Modern scientists rely on increasingly precise instruments to reveal the contours of this landscape, gradually transforming scattered measurements into detailed images of the trench and its surrounding terrain. One of the most important tools in this effort is high-resolution bathymetry, a method that measures the depth and shape of the seafloor using sound waves. Research vessels travel slowly across the ocean surface, while instruments beneath the hull send pulses of sound downward through the water. When those pulses reach the seabed, they reflect back toward the ship. By measuring the time it takes for the signal to return, scientists can determine the depth of the ocean at that location. Repeating this process thousands of times along a survey path gradually builds a three-dimensional map of the underwater landscape. Modern bathymetric systems use multi-beam sonar, which spreads many sound pulses outward in a wide fan beneath the vessel. Instead of measuring depth directly below the ship alone, this system records a broad swath of seafloor on each pass. As the ship travels across the region, the overlapping measurements combine into a detailed image of the trench walls, surrounding ridges and deep basins. These maps reveal subtle variations in the seafloor that earlier generations of explorers could not observe. Despite the power of these systems, the deepest parts of the trench still present difficulties for surface mapping alone. To reach closer to the seabed, researchers increasingly deploy autonomous underwater vehicles, often referred to as AUVs. These robotic explorers descend from research vessels and navigate through the dark waters using onboard sensors and carefully programmed routes. Because they operate much nearer to the seabed than a ship on the surface, their sonar instruments can record far finer details of the terrain. An autonomous vehicle may spend many hours moving slowly across the trench floor, maintaining a steady altitude above the sediment. During this journey, it collects thousands of measurements that reveal the shape of the basin in remarkable clarity. When the vehicle returns to the surface, scientists combine its data with information gathered by ships and satellites, gradually assembling a more complete representation of the trench. Research missions to the Mariana region continue throughout the present century. Oceanographic institutions and international collaborations organize expeditions that survey different portions of the trench and its surrounding seafloor. Each mission contributes another fragment of knowledge, adding new depth measurements and refining the maps that describe this immense geological structure. Yet even with these modern tools, the complete form of the trench remains only partly known. The basin stretches across a long section of the Western Pacific, and mapping such an enormous region requires time, careful navigation, and favorable weather conditions. Some areas have been surveyed repeatedly, revealing intricate slopes and terraces carved into the descending plate. Other sections have received only limited coverage, leaving gaps in the detailed record of the sea floor. In addition to the scale of the region, the depth itself creates technical limits. Instruments must transmit sound through many kilometers of water, where temperature, pressure, and salinity influence how acoustic waves travel. Even small variations in these conditions can affect the precision of the measurements, requiring careful calibration and repeated surveys to confirm the shape of the seabed. For these reasons, the modern map of the trench continues to evolve. Each expedition refines the picture slightly, filling blank spaces and sharpening the outlines of the deepest basin on Earth. What once appeared as a single distant measurement is gradually becoming a complex and detailed landscape, revealed piece by piece through the patient work of oceanographers studying the hidden contours of the Pacific seafloor. Along the margins of the Pacific Ocean, a vast chain of geological activity encircles the basin in a sweeping arc that stretches across thousands of kilometers. Within this immense boundary, the Earth's crust bends, fractures, and descends into the mantle in a pattern that links trenches, volcanic islands, and powerful earthquakes into a single, interconnected system. The Mariana Trench forms one segment of this larger structure, a deep curve in the ocean floor that belongs to what geologists describe as the Pacific Ring of Fire. The Ring of Fire is not a single continuous feature, but a broad belt of tectonic boundaries surrounding much of the Pacific Basin. Along these edges, oceanic plates interact with neighboring plates in ways that generate both volcanic activity and seismic movement. In many locations, the oceanic lithosphere sinks beneath another plate, creating subduction zones where the descending slab gradually moves into the mantle. Each of these zones often produces a trench along the seafloor and a chain of volcanoes rising above the subduction boundary. In the Western Pacific, the Mariana Trench represents one of the deepest expressions of this process. Here, the Pacific Plate moves beneath the Philippine Sea Plate, forming the boundary that shapes the trench. Above this descending slab, heat and chemical changes within the mantle contribute to the formation of a volcanic arc known as the Mariana Islands. These islands rise from the ocean as a curved chain of volcanic peaks, marking the surface expression of geological processes unfolding far beneath the seafloor. The relationship between trenches and volcanic arcs reflects the movement of material through the Earth's outer layers. As the oceanic plate descends, minerals within the slab release fluids that interact with the surrounding mantle rocks. These interactions encourage partial melting within the mantle above the slab. The resulting molten material rises gradually through the crust and eventually reaches the surface, where it forms volcanic eruptions that build the islands of the arc. Alongside this volcanic activity, the Ring of Fire is also known for its concentration of earthquakes. The boundaries between tectonic plates store enormous amounts of mechanical stress as the plates move slowly relative to one another. When the accumulated stress exceeds the strength of the rocks along the boundary, the crust shifts suddenly along fault surfaces. These movements release energy in the form of seismic waves that travel through the Earth, producing earthquakes that can be felt across large regions. The Mariana Trench participates in this broader network of seismic activity. Earthquakes occur along the descending slab and within the surrounding crust as the plates continue their gradual motion. Some of these events originate deep within the mantle, reflecting the ongoing descent of the oceanic plate. Others occur closer to the seafloor, where the plates interact along the subduction boundary. Viewed within the wider context of the Ring of Fire, the trench becomes part of a global system that shapes the geology of the Pacific region. Similar processes occur along the margins of Japan, the Aleutian Islands, the Andes of South America, and numerous other locations where oceanic plates descend beneath neighboring plates. Each region forms a segment of the same tectonic cycle in which new crust forms at mid-ocean ridges and older crust eventually returns to the mantle through subduction. The geological significance of this system extends beyond the Pacific Basin itself. Subduction zones influence the circulation of materials within the Earth, carrying oceanic crust and sediments deep into the mantle, where they contribute to the long-term evolution of the planet's interior. At the same time, volcanic arcs formed above these zones create new landforms and influence the chemistry of the atmosphere through volcanic gases. Within this immense framework, the Mariana Trench stands as one of the most dramatic expressions of plate convergence. Its extraordinary depth reflects the powerful interaction between plates that defines the Ring of Fire. The trench, the volcanic islands above it, and the earthquakes that occur along its boundary all represent interconnected aspects of the same tectonic process, unfolding gradually across the vast circumference of the Pacific Ocean. Across the immense span of geological time, the surface of the Earth never truly stands still. Continents shift slowly across the globe, oceans widen and narrow, and mountains rise only to be worn away again by wind, water, and gravity. Even the deepest trenches in the ocean participate in this quiet motion, shaped by forces that operate steadily across millions of years. The landscape that exists today represents only a brief moment within a much longer story. The crust of the planet forms a mosaic of plates that drift gradually upon the softer mantle below. Their movements are subtle when measured across a human lifetime, yet when these motions continue uninterrupted for millions of years, they reshape the entire face of the world. Mountain ranges provide one of the clearest expressions of this continual change. When tectonic plates collide, layers of rock can be compressed and uplifted until they rise high above the surrounding terrain. These mountains may appear permanent when viewed from the perspective of human history, but the forces of erosion begin altering them almost immediately. Rain, rivers, and glaciers slowly carry fragments of the rock away from the peaks, transporting those particles toward valleys and distant oceans. While mountains erode, new crust forms elsewhere beneath the sea. Along long volcanic ridges that extend across the ocean floor, molten material rises from the mantle and solidifies into fresh oceanic crust. As this new crust spreads outward, older sections of the seafloor drift away from the ridge and travel slowly across the ocean basin. Eventually, that older crust reaches the edges of tectonic plates, where it bends downward and descends into the mantle through subduction. This continuous cycle allows oceans themselves to change over time. Some ocean basins gradually widen as new crust forms along spreading ridges. Others begin to shrink when subduction consumes the oceanic lithosphere faster than it is created. Over tens of millions of years, these processes can alter the arrangement of continents and oceans across the entire planet. Within this broader cycle, continents periodically gather together into enormous landmasses known as supercontinents. Geological evidence suggests that such assemblies have formed and broken apart several times throughout Earth's history. Each supercontinent represents a temporary stage in the slow drift of the plates. After remaining united for many millions of years, the landmass eventually fractures as new rifts open within the crust. Oceans then begin forming between the separating fragments, initiating another phase in the long cycle of continental motion. The trenches of the deep ocean form part of this global transformation. Where plates converge, the oceanic lithosphere bends downward and disappears into the mantle. This motion allows the planet to recycle older sections of crust, returning them to the interior where they contribute to the ongoing circulation of material within the Earth. The Mariana Trench represents one of the most dramatic expressions of this process, marking a place where the surface of the planet gradually folds into its interior. Yet even this immense feature belongs to a temporary stage within the evolving structure of the Earth. As tectonic plates continue to move, boundaries shift and new configurations emerge. Over extremely long periods of time, trenches may migrate, transform, or vanish entirely as plate interactions change. The forces responsible for their formation remain active across the globe, shaping new regions while altering the structures that already exist. Seen within the context of geological time, the trench becomes part of a planet that never truly settles into a final form. Mountains, oceans, and continents participate in a slow choreography driven by the movement of the lithosphere. Each feature arises through the interaction of deep forces and then gradually evolves as those forces continue their work. The Mariana Trench, therefore, stands as one moment within this vast process. Its depth, structure, and surrounding environment reflect the present arrangement of plates in the Western Pacific. Yet, beneath the quiet waters above, the same tectonic motion continues steadily, guiding the long transformation of the planet's surface as Earth remains a restless world shaped by time. Measured against the lifetime of a human observer, the Earth appears steady and unchanging. Coastlines remain where they have always been. Mountains hold their familiar outlines, and the ocean floor seems as permanent as the sky above it. Yet beneath this sense of stillness, motion continues quietly, advancing at a pace so slow that it often escapes notice entirely. The movement of tectonic plates illustrates this difference between perception and reality. In a single year, a plate may shift only a few centimeters, a distance smaller than the width of a human hand. Such motion appears insignificant when viewed in isolation. Nothing visible changes during a single season, and even across decades, the transformation remains subtle. Over geological time, however, these tiny increments accumulate into immense change. When motion continues year after year, century after century, the total displacement grows steadily. After 1,000 years, the shift may reach several meters. After 1,000,000 years, the distance becomes many kilometers. Entire sections of ocean floor drift across the planet, carrying continents, island arcs, and deep trenches with them. This gradual accumulation creates a world that evolves continuously while appearing stable in the short term. The seabed that now forms the Mariana Trench has traveled across the Pacific Basin for tens of millions of years before reaching its present position. Each year of motion contributed only a small adjustment, yet together, those movements produced the vast tectonic structures that shape the region today. Geological time therefore operates on a scale that differs greatly from everyday human experience. A span of 1,000,000 years, which may seem almost unimaginable from a personal perspective, represents only a brief interval in the life of the planet. Mountains may rise and erode within such a period, and ocean basins may widen or narrow as tectonic plates continue their slow migration. This difference in scale creates an illusion of permanence. Landscapes appear stable because their changes unfold gradually across intervals far longer than a human lifetime. A coastline that remains unchanged for centuries may still be part of a larger transformation unfolding across tens of millions of years. The forces responsible for shaping the Earth work patiently, guiding the motion of plates and the circulation of material within the planet's interior. The trench itself reflects this steady accumulation of change. Each small movement of the Pacific Plate carries new sections of seafloor toward the subduction boundary. Over immense spans of time, these incremental steps deepen the trench, adjust its contours, and alter the structure of the surrounding crust. None of these changes occur abruptly from year to year, yet the long record of plate motion reveals their gradual influence. Human perception tends to focus on events that happen quickly, such as earthquakes or volcanic eruptions. These sudden moments capture attention because they occur within the time frame of a human life. Yet even these dramatic events represent brief expressions of deeper processes that have been unfolding quietly for millions of years. When viewed within the full span of geological time, the Earth appears less like a fixed landscape and more like a slowly evolving system. Continents drift, ocean floors move, and deep trenches adjust their shape as tectonic forces continue their work beneath the surface. Each year adds another small movement to this ongoing transformation. The Mariana Trench therefore exists within a world defined by gradual change. What seems stable across human history is part of a longer sequence of motion stretching far into the past and continuing far into the future. The slow pace of tectonic movement conceals its power, allowing the surface of the planet to transform steadily while maintaining the quiet appearance of permanence. Despite decades of research and exploration, the deepest trench in the ocean still holds many details that remain uncertain. Scientists have measured its depth, mapped much of its structure, and observed its environment through submersibles and robotic vehicles. Yet the trench extends across a vast region of the Pacific, and the extreme conditions at its floor limit how frequently and how closely researchers can study its landscape. Each expedition reveals new information, but also highlights how much remains beyond direct observation. One challenge arises from the incomplete nature of existing measurements. Although modern bathymetric surveys have mapped large portions of the trench with remarkable precision, many areas have been explored only once or only from a distance. Sound waves used for mapping must travel through many kilometers of water, and small variations in temperature and salinity affect the speed at which those signals move. These variations introduce subtle uncertainties into the depth calculations, requiring repeated surveys to confirm the measurements. As a result, even the exact depth of the deepest point continues to be refined. Different research missions sometimes report slightly different values, depending on the instruments used and the conditions present during the survey. These differences are usually small when compared with the overall depth of the trench, yet they illustrate how difficult it can be to measure such extreme environments with absolute precision. Beneath the sediment that blankets the trench floor lies another layer of uncertainty. The internal structure of the crust and the descending slab remains only partly understood. Seismic imaging provides valuable information about the broad geometry of the subducting plate, but the finer details of fractures, mineral transformations, and fluid pathways within the rocks are harder to resolve. These microstructures influence how the lithosphere bends, breaks, and gradually descends into the mantle. Scientists continue to investigate how these small-scale features shape the behavior of the subduction zone. Tiny variations in rock composition or fluid content can alter the strength of the crust and affect how stress accumulates along the plate boundary. Because direct sampling of these depths remains extremely difficult, researchers rely on indirect methods such as seismic waves and computer models to infer the conditions within the Earth. Future technology may allow more detailed exploration of these hidden structures. Advances in autonomous underwater vehicles, deep-sea sensors, and long-term monitoring instruments offer new ways to observe the trench environment. Some research groups are developing instruments capable of remaining on the seafloor for extended periods, recording subtle changes in seismic activity, pressure, and temperature. Over time, these measurements may provide clearer insights into how the trench evolves. Improved mapping technologies may also reveal additional details about the shape of the basin itself. Higher resolution sonar systems and more precise navigation tools allow scientists to examine smaller features on the seafloor, including ridges, terraces, and sediment flows that were previously invisible in broader surveys. As these instruments continue to improve, the trench may gradually appear in greater clarity. Even with these advances, the trench remains part of a dynamic system that continues to change over time. The interaction between tectonic plates, the movement of sediments, and the slow descent of the oceanic slab all contribute to a landscape that evolves gradually. Understanding these processes requires observations gathered across long intervals, often longer than a single research expedition can provide. For this reason, the Mariana Trench still contains questions that scientists have yet to answer completely. Researchers continue to refine measurements of its depth, investigate the internal structure of the subduction zone, and study the geological processes occurring beneath the seafloor. Each new mission contributes additional pieces to this evolving picture. The deepest part of the ocean, therefore, remains both a place of discovery and a reminder of the limits of current knowledge. Even after decades of exploration, the trench continues to offer mysteries shaped by distance, pressure, and the immense scale of the Earth's geological systems. At the far edge of the Pacific, beneath miles of water and layers of unseen stone, the deepest part of the ocean continues its quiet transformation. Nothing there is fixed in a final shape. The trench exists within a restless boundary where immense sections of the Earth's crust meet and slowly move past one another. Though the seafloor may appear motionless when viewed from a descending submersible or a distant sonar trace, the landscape is part of an ongoing process unfolding beneath the ocean. The forces shaping this region work with patience, measured not in years or centuries, but in spans of time far longer than human history. The crust of the Pacific Basin drifts gradually toward the boundary, carrying with it ancient fragments of seafloor formed thousands of kilometers away. As this motion continues, the plate bends downward and begins its descent into the deeper interior of the planet. Each small movement contributes to the slow reshaping of the trench. Around this boundary, the structure of the seafloor adjusts continuously. Sediments settle through the water column and accumulate in the deepest basins. Subtle shifts occur within the rocks beneath the surface as pressure, temperature, and chemical reactions alter their internal structure. The descending slab continues its journey into the mantle, while the surrounding crust responds with gentle flexing and adjustment. These changes unfold gradually enough that they rarely reveal themselves in dramatic ways. Most of the time, the trench remains a quiet environment where movement is too slow to notice directly. Yet within the immense timeline of geological history, these small adjustments accumulate just as steadily as the motion of the plates themselves. Over millions of years, the shape of the trench evolves, its contours shifting as the Earth redistributes mass through the slow circulation of its outer layers. Seen from this broader perspective, the trench becomes part of a living boundary rather than a static depression in the seafloor. The plates that meet here carry the history of distant volcanic ridges and ancient ocean basins. As they converge, they guide fragments of the planet's surface back toward the mantle, where those materials will eventually be transformed and recycled through deeper geological processes. The quiet activity within this boundary also connects the trench to larger systems shaping the planet. Movements in the mantle influence the strength and behavior of the lithosphere above. Variations in heat and pressure guide the slow bending of the crust. Even the accumulation of sediments and the circulation of ocean water play subtle roles in the evolving structure of the seafloor. None of these influences act alone. Together, they create a complex interaction that continues long after any single observation has ended. The trench, therefore, represents more than a measurement of depth or a distant location on a map of the ocean floor. It reflects an ongoing conversation between the surface of the Earth and the interior forces that shape it. Within this immense timescale, the deepest place in the ocean is not a finished feature carved once and left unchanged. It is a stage within a much longer sequence of transformations. Plates continue to move, rocks continue to bend and adjust, and sediments continue to settle across the basin floor. From the calm darkness of the trench floor to the shifting plates far below, the entire system moves slowly but continuously. The Earth reshapes itself without urgency, guided by forces that have operated since long before the oceans and continents reached their present forms. The deepest place on Earth therefore carries a quiet lesson about the nature of the planet itself. Beneath the stillness of the ocean, the crust continues its patient motion. The trench remains part of a living boundary where the surface of the Earth slowly folds back into its interior. The deepest place on Earth is not a finished sculpture, it is a process.